This video is about separable differential equations. If you appreciate this content, please give it a like. Example 1 is a separable differential equation because there is a way to get all of the y factors on the left and all of the x factors on the right. We can start by multiplying both sides of this equation by dx. That will leave us with dy on the left, and this is equal to x squared y dx. To move this y factor to the left, we will divide both sides of the equation by y. So on the left, we will now have 1 over y dy is equal to x squared dx. Now we can integrate both sides of the equation. On the left side, we are integrating with respect to y, and on the right side, we are integrating with respect to x. We know that the antiderivative of 1 over y will be natural log absolute value of y. Normally we would say plus c, but we will save that for the right-hand side of the equation. On the right-hand side, we can integrate using the power rule of integration. Adding 1 to this exponent gives us x to the third power, and dividing by the new exponent gives us a 1/3 in the front. And now we do the plus c. This is the general solution to the differential equation. General means that we don't have to find the value of c. The directions did not say that we had to find the solution in the form y equals f of x, but often the directions do say that. So let's practice this. That means we have to get y by itself in this equation. We can eliminate the natural log part by dropping a base e on both sides of the equation. The base e and the ln cancel each other out. These are inverse functions. So now we have this. We can take away the absolute value on the left-hand side as long as we make the right-hand side plus or minus. So this is another version of the answer in the form y equals f of x. There's one more version I'd like to show you because you might run into it on a multiple choice question. But first, a quick side lesson. When you multiply with like bases, you add the exponents. So this would be e to the b plus c power. But surely you can see that this process is reversible. So if you had e to the b plus c power, you could rewrite this as e to the b times e to the c. And that is exactly what we have right here. So we can rewrite the right-hand side of this equation as plus or minus e to the 1/3 x to the third power times e to the c. We can simplify this further because we know that c is just an unknown constant, and e to the c is just another unknown constant. Let's call it d, and I'm going to put that d here in the front. So another version of the answer in the form y equals f of x is y equals plus or minus d times e to the 1/3 x to the third power. On example 2, we will again use the property that I showed you in example 1, where you can take e to the b plus c power and rewrite that as e to the b times e to the c. E to the 2x plus 5y power is the same as e to the 2x times e to the 5y. Now, we need to have all of the y factors on the left and all of the x factors on the right. We can multiply both sides of this equation by dx. That's going to move the dx to this side. But simultaneously, I'm going to divide both sides by e to the 5y. So on the left side, I'm going to have 1 over e to the 5y dy is equal to 3 e to the 2x dx. But actually, I would rather write this as e to the negative 5y power. Now that we have separated the variables, we can take the antiderivative of both sides of the equation. On the left side, I'm going to do a mental u substitution. U is negative 5y. U prime is negative 5. We can integrate with respect to u instead of y as long as we divide by u prime. So I need to divide by negative 5 by putting negative 1/5 out in the front. Other than that, I'm thinking, what's the antiderivative of e to the u? Well, it's just e to the u, e to the negative 5y. We will save the plus c for the other side. For those of you who are not comfortable with mental u substitution, I'm going to go back and show it. So we are letting u equal the negative 5y, therefore u prime is negative 5. So making that substitution, we have the antiderivative of e to the u, and instead of dy, we put du over u prime, so du over negative 5. Of course, we can put this negative 5 that's in the denominator out in the front as negative 1/5. So now we have this. We will now use the memorized rule that the antiderivative of e to the u is e to the u. So that's why we get negative 1/5 e to the u plus c, but again we will save the plus c for the right hand side. But of course, instead of writing the u, we will substitute back in negative 5y. So this is how you would handle the left side of the equation if you were going to show the u substitution instead of just doing it mentally. I'm going to again do mental u substitution with the right hand side, but first I'm bringing down this 3. I'm thinking of the 2x as u. I can integrate with respect to u instead of x as long as I divide by u prime. If u is 2x, then u prime is 2. So I need to divide by 2 by putting a 2 under the 3 that's out in the front. So now I can take the antiderivative of e to the u, and that will be e to the u. But I'm not going to write the u, I'm going to continue to write 2x. And this time we will put the plus c. For kids who are uncomfortable with mental u substitution, it would work like this. Let's let u equal 2x. Therefore, u prime is equal to 2. So we have the antiderivative of 3e to the u, and instead of dx, we put du over u prime. We can move the 3 and the 2 out to the front as 3 over 2, and we have the integral of e to the u du. The integral of e to the u is just e to the u. So we bring down the 3 over 2, and we put e to the u, but we suddenly remember that u is 2x, and then we put the plus c. So that's exactly what we got without showing the work a minute ago. This is a valid solution if they don't ask us to find the solution in the form y equals f of x. But they usually do. So let's practice and get y by itself. We can cancel out the negative 1/5 by multiplying both sides of the equation by negative 5. That will leave us with e to the negative 5y power on the left. Multiplying the right side of the equation by negative 5 will give us negative 15 over 2 e to the 2x, but then distributing we will have minus 5c. c is just a random constant. Negative 5c is just another unknown constant. So let's go ahead and replace this with the letter d. We can cancel out the e by taking the natural log of both sides of the equation. So let's do ln on both sides. So the natural log and the base e cancel each other out, leaving negative 5y on the left-hand side. So negative 5y is equal to all of this. And then finally we divide both sides of the equation by negative 5. So this is the general solution in the form y equals f of x. You don't have to make this substitution with the d. So if you still have a minus 5c right here, that's fine. For example 3, we can move the sine 4y over to the left by multiplying both sides of the equation by this denominator. At the same time, we will multiply both sides by dx. So on the next step, we will have sine 4y dy is equal to cosine 3x dx. Now that we have separated the variables, we can integrate both sides of the equation. Let's use our mental u substitution. Let's let u be 4y on the left side. Therefore, u prime is 4. We can integrate with respect to u as long as we divide by u prime. So we are going to have a 1/4 right in the front. The antiderivative of sine is negative cosine. So we'll have negative 1/4 cosine 4y. We will save the plus c for the other side. Let's find the antiderivative of the right-hand side using u substitution again. In this case, u is 3x and u prime is 3. You can take the integral with respect to u instead of dx as long as you divide by u prime first. So that's why I'm going to have a 1/3 in the front. Now, the integral of cosine u is sine u plus c. By the way, when I take the antiderivative of cosine u, I'm asking myself the derivative of what is equal to cosine u. We know the derivative of sine u is cosine u. That's why the antiderivative is sine u. Similarly, when I needed to find the antiderivative of sine u on the left side of the equation, I asked myself the derivative of what is sine u. I know that the derivative of cosine is negative sine. That's close. So the derivative of negative cosine will be positive sine. That's why the antiderivative was negative cosine. Anyway, we need to solve this for y. So let's start by getting rid of the negative 1/4 by multiplying both sides of the equation by negative 4. On the left, that will cancel out the negative 1/4 and leave me with the cosine of 4y is equal to. Now, multiplying by negative 4 right here will give me negative 4/3 sine 3x. Oh, we need to multiply this by negative 4 as well. So this will become negative 4c. Our goal is to get y by itself. In order to cancel out the cosine, we need to take the arc cosine of both sides of the equation. On the left side, the arc cosine and the cosine will cancel each other out and leave behind just the 4y. I'm going to recopy all of this. Notice that I went ahead and replaced the negative 4c with the letter d because negative 4c is just another constant, so we might as well call it d. Finally, we can get y by itself by dividing both sides by 4. So this is the final answer to example 3. In example 4, we are being asked to find the particular solution to the differential equation given an initial condition. So that means we will find the value of the constant of integration, c. We can separate the variables by multiplying both sides by y and multiplying both sides by dx. Now that we have separated the variables, we can take the antiderivative of both sides of the equation. On the left side, we will use the power rule. Increasing the power by 1 gives us y squared. Dividing by the new power gives us a 1/2 in the front. We will save the plus c for the right-hand side. On the right-hand side, we can take the antiderivative term by term. The antiderivative of x is 1/2 x squared, and the antiderivative of 1 is simply x. And now we do the plus c. Here's where we use the initial condition to find the value of c. We will substitute 0 for the x's and -2 for the y. On the left side, -2 squared is 4, and half of 4 is 2. So we have 2 equals. We can disregard the 0 terms, and actually c is equal to 2. Substituting 2 back in for c gives us this. We need to do a little bit of basic algebra to get y by itself. Let's multiply both sides of the equation by 2. So on the left side, multiplying by 2 leaves y squared is equal to. On the right-hand side, multiplying by 2 cancels out the 1/2, so that's x squared. Multiply by 2 again, that's 2x. Multiply by 2 here, and that is 4. Now we need to take the square root of both sides of the equation. So that will give us y is equal to plus or minus the square root of x squared plus 2x plus 4. However, only one of these is the actual answer. It's either positive square root of x squared plus 2x plus 4 or negative square root of x squared plus 2x plus 4. Which one is correct depends on the initial condition. Notice that f at 0 is -2. It's a negative number. The square root part can only give you a positive value. There's nothing that you can plug inside of a square root that will give you a negative number. So this part is definitely positive. So if f at 0 is to be -2, there's going to have to be a negative in the front. So the answer is specifically y equals negative the square root of x squared plus 2x plus 4. Example 5. Find the particular solution y equals f of x to the differential equation given an initial condition. We can separate the variables by dividing both sides by y to the third power. Rather than writing 1 over y to the third power, let's write y to the -3 power. So on the left-hand side, we will have y to the -3 dy. Let us also multiply by the dx. So this will equal x dx. Now that we have separated the variables, we can take the antiderivative of both sides of the equation. On the left side, we can just do the power rule of integration and add 1 to this exponent. That will give us y to the -2 power. Dividing by the new exponent gives us a -1/2 in the front. We will save the plus c for the right-hand side. And power rule right here will be 1/2 x squared, and there's your plus c. Here's where we use the initial condition to find the value of c. So go ahead and say at the point 1, 2, and then substitute 1 for x and 2 for y. So now we have this. To do 2 to the -2 power, we need to drop this down to the denominator. So I'm going to keep the 1/2 for a minute. This is going to be 1 over 2 squared. This is 1 over 4. And 1 squared is 1, so we have -1/2 times 1/4 is equal to 1/2 plus c. Negative 1/2 times 1/4 is negative 1/8. To get c by itself, we need to subtract 1/2 from both sides. So we will have negative 1/8 minus 1/2 is equal to c. Negative 1/2 is the same as 4 over 8. So we have negative 1/8 minus 4/8 is equal to c. Negative 1/8 minus 4/8 is negative 5/8. So c is equal to negative 5/8. Let's substitute this value back in for c. Now we just need to do some algebra to get y by itself, starting by multiplying both sides of the equation by negative 2. The multiplying by negative 2 will cancel out the negative 1/2, so on the left-hand side we have y to the negative 2 power. Multiplying by negative 2 over here will leave us with negative 1 x squared. And look, if I multiply by negative 2 right here, a negative times a negative is a positive. And 2 will divide into 8 4 times. So this will be plus 5 over 4. In order to cancel out the negative 2, we need to raise both sides of the equation to the negative 1/2 power. When you raise a power to a power, you multiply, and negative 2 times negative 1 makes 1. So those cancel out, and on the left-hand side, we just have the y. So what you see on the right-hand side is the answer. Maybe I'll just show it. So one version of the answer would look like this. But we can also drop this expression down to the denominator and even put it inside a square root. So here's another version of the answer. Example 6. Consider the differential equation dy dx equals y minus 1 over x squared, where x is not equal to 0. Find the particular solution y equals f of x to the differential equation with the initial condition f at 2 equals 0. To separate the variables, we begin by multiplying both sides by 1 over y minus 1. On the right-hand side, the y minus 1's cancel out, leaving behind 1 over x squared. Of course, we will next multiply both sides by dx to move the dx to the right-hand side. Now that we have separated the variables, we can integrate both sides of the equation. Technically, I'm doing a mental u substitution to find the antiderivative on the left side of the equation. I'm thinking of this as 1 over u. If u is y minus 1, then u prime is just 1. So I can just go ahead and take the antiderivative with respect to u. We know that the antiderivative of 1 over u du is the natural log of the absolute value of u. That's our memorized rule. So let's do that right now. This will be the natural log of the absolute value of u. Normally we would have to divide by u prime, but in this case u prime is 1, so dividing by u prime doesn't change anything. On the right-hand side, I'm going to think of this as x to the negative 2 power, so I can do the power rule of integration. Adding 1 to this exponent gives me x to the negative 1 power. Dividing by the new exponent gives me a negative sign out in the front. And don't forget the plus c. Now it's time to use the initial condition to find the value of c. Let's plug in 2 for x and 0 for y. This negative x to the negative 1 power is the same thing as negative 1 over x. And substituting in the 2, we have negative 1/2 plus c. The natural log of the absolute value of negative 1 becomes the natural log of positive 1 because we took the absolute value. And the natural log of 1 is 0. we have 0 is equal to negative 1/2 plus c. Adding 1/2 to both sides gives us c is equal to positive 1/2. Substituting 1/2 back in for c gives us the natural log of the absolute value of y minus 1 is equal to negative 1 over x plus 1/2. We need to get y by itself now, and we can cancel out the natural log by dropping a base e on both sides of the equation. On the left side, the base e and the natural log will cancel each other out because these are inverse operations. That will leave behind the absolute value of y minus 1 on the left. And on the right, we have what you see here. We can take away the absolute value on the left-hand side as long as we make the right side of the equation plus or minus. Now we can get y by itself by adding 1 to both sides. I'm going to put the 1 in the front. This expression represents two possible solutions to the differential equation, one with the positive and one with the negative, but only one version is correct. Which one is correct depends on the initial condition. We need to pick the version such that if we plug in 2 for x, we will get 0 for y. So let's see, if we plug in 2 for x right here, then we have negative 1/2. Negative 1/2 plus 1/2 is going to be 0. E to the 0 power is 1. So the right-hand side of the equation is going to be a 1. In order for the result to be 0, we need 1 minus 1. Obviously 1 plus 1 would be 2, not 0. So that's how we know to use the negative version of the equation. And that's it. So the solution to the differential equation that satisfies the initial condition is this. Example 7. Let v of t be the velocity in feet per second of a skydiver at time t seconds, t greater than or equal to 0. After her parachute opens, her velocity satisfies the differential equation dv dt equals negative 2v minus 32. With the initial condition, v of 0 is equal to negative 50. Use separation of variables to find an expression for v in terms of t, where t is measured in seconds. Let me emphasize that you cannot separate variables by adding and subtracting. For example, we cannot add 2v to both sides to move the v's to the left and think you're going to get 2v dv dt is equal to negative 32. That doesn't work. Over here, this 2v is now multiplied. You didn't really add it, so this is bad algebra. We will only separate these variables by multiplication and division. Let's start by multiplying both sides by the dt. So that will give us dv on the left is equal to negative 2v minus 32 times dt. But we need the v's on the left, so we're going to divide both sides of the equation by this entire expression. Now we have this. You can put a 1 here if you feel bad that dt is all by itself. Aw. Now that we have separated the variables, we can integrate both sides of the equation. But I think I would like to factor out the common factor of negative 2 from the denominator. For a brief moment we have this, but we realize that we can take this negative 2 out of the denominator and put it out front as a negative 1/2. Whoops, I forgot the dv for a second there. So now we can integrate the left side of the equation by doing a little bit of mental u substitution. I'm going to think of this as 1 over u. So u is v plus 16 and u prime is 1. Since u prime is 1, I don't need to worry about dividing by u prime like I normally do, and I can just integrate with respect to u. We know that the integral of 1 over u du is equal to the natural log of the absolute value of u plus c. So on the left side we have negative 1/2 times the natural log of the absolute value of u, and we'll save the plus c for the right hand side. The antiderivative of 1 is t. And there's your plus c. It's time to use this initial condition to find the value of c. Let's plug in 0 for t and negative 50 for v. Now we have this. Negative 50 plus 16 is negative 34. And of course the absolute value of negative 34 is positive 34. Let's substitute this value in for c. Now we just need to use our algebra skills to get v by itself. Let's start by multiplying both sides of the equation by negative 2. So the negative 1/2 will cancel out, leaving behind the natural log of the absolute value of v plus 16 is equal to negative 2t, and this negative 1/2 will cancel out and become just a positive 1. So we have plus the natural log of 34. We can cancel out the natural log by putting a base e on both sides of the equation. On the left side, the base e and the natural log cancel each other out. So we have the absolute value of v plus 16. I need to give a quick side lesson to remind you how I'm going to simplify this. I'm noticing that we have a base e, and then somewhere in the exponent we also have a natural log. To simplify, we need to get these next to each other. So here's the quick side lesson. We know that e to the a times e to the b would be e to the a plus b. But this is reversible. If we have e to the a plus b, we can always rewrite this as e to the a times e to the b. So the right hand side of this equation is just like e to the a plus b. So we can rewrite this as e to the negative 2t times e to the natural log 34. Now the base e and the natural log are right next to each other, so these can cancel each other out. So on the next step I'll just have a 34, and we'll put that in the front. So now we have this. We can remove the absolute value from the left hand side as long as we make the right hand side positive or negative. Only one of these is correct, but let's go ahead and subtract 16 from both sides first, and then we'll worry about it. So I'm going to put the negative 16 in the front, and for a brief moment we will write plus or minus 34 e to the negative 2t. Make sure you don't do some bad algebra right here. These cannot be combined in any way. To decide whether it should be positive or negative, we need to make sure that we are satisfying the initial condition that says if t is 0, the value of velocity should be negative 50. So if we put in 0 for t, we will have e to the 0 power, which is 1. So we're going to have negative 16, and it's going to be plus or minus 34. We need the result to be negative 50. To make the negative 50, we need minus 34 here instead of plus 34. So that's how we know to use the negative version of this solution. So this is the solution to the differential equation that satisfies the initial condition. One more time, please do not try to combine these together. That's bad algebra. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.